Hi, myself Karthik Vaidyanathan. I'm a computer science PhD student at Gran Sasso Science Institute in Italy. In this video, I would like to talk about our work, Quantitative Verification Aided Machine Learning, a tandem approach for architecting self-adaptive IoT systems. This work was done as a joint collaboration with Professor Javier Camara from University of York and Professor Henry Muccini from University of L'Aquila. We live in a world of Internet of Things. As per the latest statistics, each second 127 new devices are connected to the internet. This means that the architecture behind these systems has to be really good so as to guarantee the quality that they promise. But this does not come for free. There are a lot of challenges that exist in architecting an IoT system. Some of those challenges are heterogeneity due to the different types of devices involved, ensuring the quality of service, interoperability due to different types of communication protocol, and the list goes on. Two of the key quality of service challenges are that devices might run out of battery due to resource constraint. It is expected that ICT is going to consume 21% of world's electricity by 2030. Similarly, performance issues can arise due to the generated traffic. It is also expected that this traffic might contribute in a tremendous way towards global carbon footprint. So these two are considered to be two of the key quality of service challenges that exist in architecting IoT systems. Let us put this in perspective. Let us consider a scenario. So we have an event called NDR, which happens in the city of L'Aquila. NDR basically stands for Notte di Ricercatore. It is a researchers' night event. In this event, researchers and public are brought together for participating in various kind of information and entertainment events. This event happens throughout the city, so you can see the, the map of the event here, and it happens throughout the city center. There are a lot of indoor events as well as outdoor events. We also have an app which can be downloaded from the below link, and here people can actually see which venue, what kind of events are happening, what are the venues where events are happening, etc. Now, some of the observation that we have in the past years is that 25,000 people attend this event every year. Late hours are more crowded than early hours. Then, weather condition affects user preferences. The most important thing is crowding happens in the city center. This is because since this event happens and it's a one-day event, um, there are shortages of parking lots, and also people find it difficult to identify the venues which are full or which venues are free, etc. This causes a congestion in the city center. To avoid this, our team has been invited to create an IoT based solution which basically helps people with identifying free parking lots as well as free venues. The figure shows the overall architecture of the envisioned system. As you can see, it uses different kinds of sensors at the parking lot as well as at the venue entrances and exits to redirect people by displaying it on the displays located at the venues and parking lots. All the sensors operate in two different modes. One is a normal mode and another is a critical mode. Normal mode is when the scenarios is completely fine. It's like a normal operation where the number of people are less entering the venues or entering the number of cars entering the parking lots are less. Critical mode is when then there is a sudden surge of people entering the venues or people entering the parking lots. This means then the sensors has to communicate to the display at a much higher frequency. So we have two types of mode in this case. Of course, in another scenario, there can be multiple modes as well. So what are the constraints that we have in NDR? One is we don't have an availability of an external power source, because since it's a one-day event, most of the venues are created in an ad hoc way, or even the parking lots. So the sensors cannot resort to an external power source. So we have to use battery powered sensors, which means that we have to ensure that they stand longer. Okay, now one of the easiest way to ensure that they stand longer is to reduce the communication frequency. But if you reduce that, it can affect the service accuracy. Third is you cannot even have high traffic because it can lead to congestion and thereby impacting the performance. So we need to ensure that the system is able to maintain that in between position of not consuming too much energy and not consuming too much traffic or too much less traffic. So in a mathematical formulation, we can say that the overall goal is to maximize a utility u tau for a time period tau such that u tau is equal to we into e tau plus wd into t tau, where e tau and t tau are basically piecewise function, which denotes the energy and traffic savings respectively. Dmax basically denotes the maximum traffic that the system can consume in a given time interval. Dmin denotes the minimum traffic that the system has to maintain for a given time interval. Emax denotes the maximum energy the system can consume for a given time interval. Based on this, we calculate the utility, and we need to ensure that we have to maximize this utility so as to ensure that the system stays within the limits. What are the possible solutions and issues? Of course, we can use self adaptation techniques to guarantee quality of service constraints. But then the question is, what kind of self adaptation techniques to be used? We can use proactive adaptation techniques. Why? Because there has been attempts to use different kinds of reactive adaptation mechanisms, and it has been found in the literature that they always end up in suboptimal adaptations. Now, if you have to use proactive adaptation techniques, there has been attempt to use techniques like quantitative verification. But the problem is when the scale of the system is really big, as in the case of IoT systems, this might not work well. Moreover, they are not found to be really efficient in predicting the quality of service evolution. So for this, we can use machine learning techniques. Using the quality of service data, they can learn from it and predict the expected quality of service. But is that it? What about the problem of learning bias and accuracy? So, machine learning, of course, has its own problem, and there is now a big research going on in understanding the fairness concept of in machine learning. So, what can be the impact? Incorrect decisions by machine learning can lead to suboptimal adaptations again, and this can have a big impact on the quality of service. Also, the execution of the system itself can be affected. So, we need to avoid this. How can we do that? Solution is to use quantitative verification there. So let us use something like a probabilistic model checking technique which can ensure that only feasible adaptations are executed. So what is the process? The process is machine learning can make the decision and quantitative verification can check if the decision is good. Now, once it checks, it can provide the feedback back to the machine learning. Using this, machine learning can continuously get the feedback and it can converge over a period of time towards optimal solutions. So this is the basic concept. The issue that still remains is what kind of adaptation techniques can be used. Of course, as I said, we cannot do simple reconfiguration like manipulating the data traffic value, etc. So we have to resort to structural adaptation techniques. Three different architectural patterns for self-adaptation in IoT has been proposed in literature. This include synthesize utilize, which is a completely decentralized pattern, synthesize command, which is a completely centralized pattern, and collect organize, which is a semi-decentralized pattern. So now the question is, then why not just use one of these patterns? Well, the answer is no, because each pattern has their own trade-off with respect to energy and data traffic values, and this depends upon the operational context of the system. So our system should be intelligent enough to understand which pattern to be used based on the usage context. This is where our approach can really help. So what is the basic intuition behind our approach? Identify the need for adaptation, then let machine learning select a pattern based on the operational context. Now once it has selected, allow quantitative verification to verify if the pattern selected is the right pattern to be used. If yes, apply it and execute the adaptation. If no, again go back and ask machine learning to produce a different decision. So this no decisions and yes decisions can be given as feedback to machine learning to converge towards optimal solutions. Okay, how does our approach look like? Our approach is basically based on the MAPE loop. So it has a monitor activity which keeps collecting the quality of service data as well as the sensor data from the IoT system. This data is then passed into the analyze activity, which uses machine learning models to predict the expected quality of service. These machine learning models are available from the knowledge base, where the machine learning models are updated time to time by the machine learning engine. Machine learning engine basically collects quality of service data on a periodic basis from the monitor activity, and this is then used to create machine learning models for prediction. Then we have a plan activity which consists of two components: decision selector, which selects the best adaptation pattern to be used using machine learning technique, and a decision verifier which uses quantitative verification to verify if the decision selected is feasible or not. Then, based on this decision, the adaptation strategy is communicated to the execute component which executes the adaptation. In this work, we are going to focus more on the plan activity as well as the execute activity. In particular, let's look how decision selector and decision verifier works. So the figure shows the overall decision making process flow. Decision selector, as I said, uses machine learning technique to select the best adaptation pattern to be used. Decision verifier then sees if this pattern can be applied or not. So the first step with decision selector is to identify the expected quality of service state. So the course state identifier, in other words, uses two information. One is the course goals, then is the course forecast. Let's see what it is. But before that, we need to understand two terminologies. One is a horizon H and another is decision period tau. Horizon is the time interval for which a prediction is made, and each of the horizon is divided into multiple decision periods. This idea is basically inspired from the field of model predictive control. Now, then what is quality of service goal? Quality of service goal basically defines the threshold for each of the quality of service attribute. For example, GE is equal to energy, 10, 20 means that the energy has to be between 10 and 20. So 20 is the maximum and 10 is the minimum. Similarly, GD equal to traffic, 300, 500 means that the system has to maintain the data traffic between 300 and 500. Okay, so then what is course forecast? Course forecast is basically a pair which denotes for each of the course attribute what is going to be the expected value for the horizon H. So QFE equal to energy, 10 denotes that the expected energy is going to be 10 joules for the next horizon period. Okay, then what does course state identifier do with this? Course state identifier takes this course forecast, it takes this course goals, it creates a mapping between the forecast and the goals. How is it done? For example, let's consider that the course forecast is energy 15 joules and traffic is 200 messages for that given decision period. Then it can create a mapping based on the goal such that there are three categories, low, medium and high, and based on the goal it can map this into each of these categories. So for example, energy belongs to a medium category because it is 15 joules and it falls between 10 and 20. Then traffic belongs to a category of low because it is less than 300, and this forms the expected course state. This state is then sent to the pattern selector for further processing. Pattern selector then uses the course state to identify the best pattern to be used. For this, it uses reinforcement learning technique, in particular Q-learning. So Q-learning is basically a model-free learning technique. So no pre-training is required. It is just as simple as what is denoted in the figure. There is an agent, it interacts with the environment by performing an action. In our context, this agent is an IoT system. The action is basically switching to a pattern. Environment is nothing but the quantitative verification. So once it performs the action, it changes the state from one state to another. In our case, it changes the state from one core state to another core state. And for reaching every core state, it gets a reward R. A reward R. So state space basically consists of the set of possible combination of the course category along with the patterns. Actions, on the other hand, is a set of A1, A2, AM where each AI denotes a switch to a pattern I. Rewards is nothing but a mapping function that maps every state to an integer value. And then we have a Q table, which is also the brain of the Q learning algorithm. It is a state by action matrix where each S, A pair denotes the significance of reaching a state and performing an action A from that state. So this is the pattern selector algorithm. It basically uses the parameters, states, actions, expected course state, the pattern P, the reward function rho. Then it uses two additional parameters. One is alpha, which is also called the learning rate. It denotes the importance given to the observation learned at every step. And gamma is the discount rate. It denotes how much importance has to be given to the next action. Then it identifies the state from EQ and P, then it selects the action, it assigns the reward. Then what it does is very important. What it does is it identifies what is the state that it has to go given the current situation. So given the fact that the system is in a particular execution state, it has to select the action in such a way that it goes to that state which gives the maximum benefit. This is what happens in step number 5. And based on this, it updates the queue table in step number 6, and the selected pattern is then sent to the configuration generator component. The role of the configuration generator is to get the pattern P from the pattern selector and create the configuration in such a way that it can be parsed by the CTMC model generator. So in order to perform the model checking, we need to understand how the system is expected to evolve in the next horizon. For this, it uses forecasts. So what are these forecasts? So as I said in the NDR case study, every sensor can be in a normal mode and as well as in a critical mode. So let's suppose that a decision or a horizon period is 10 minutes and we have a forecast like this. This means that sensor is expected to be in normal mode from 0 to 100 second, and then it is going to be in critical mode from 101 to 600 seconds. So this allows us to identify what will be the expected behavior of the sensor for the next decision period. This can be further sent to the model generator. So what the configuration generator does is it fetches the static pattern configuration from the pattern repository, this repository. This repository basically contains for every pattern, for every sensors and other components involved, what is the expected energy consumption for sending a message? What is the expected energy consumed for receiving a message? All this information are encoded in the pattern repository. This is further enriched with this dynamic information based on the forecast received, and this is then sent to the CTMC model generator. CTMC model generator basically gets the configuration JSON and then it converts it into a CTMC model, continuous time Markov chain model with all transition probabilities and states. Okay, but let us recall the different architectural patterns that we have. Now, in every pattern, we can associate to every component a particular process type. So, for example, sensors in synthesize utilize can send data to other sensors as well as it can receive data from other sensors. Similarly, database is just going to get the data from the sensors. On synthesize command, sensors can send the data to database, and of course database can forward this to other sensors or display units as well. This is the similar is the case with the collect organize. So every component in the pattern can be mapped to a process type. This table denotes such a mapping. So for every pattern, for every component, sensor, database, controller, display, we can have a process type. Now we instantiate the process types for each component in the pattern. As I said, in synthesize utilize, the sensor can be mapped to a produce forward process type. And each of the sensor can be in a normal mode or in a critical mode. In normal mode, it sends the message with the rate lambda n, and in critical mode, it sends the message with the rate lambda c. For each message sent, there is an energy consumption ES, and for each message received, there is an energy consumed ER. Now, each message sent or received contributes to a traffic of 1 unit. This is the same for each process type. Now, all process instances are now combined or composed using standard CSP composition to obtain a CTMC model of the configuration behavior. This CTMC model is then sent to the model checker. Now, what we have to do? Now we have the model. Now we need the model checker to say what is going to be the expected coarse values. Based on this, we need to see if the adaptation is feasible or not. So the model checker basically quantifies the expected coarse values for each of the attribute over the horizon edge. It uses CSL formulas for achieving this. CSL is basically a probabilistic temporal logic which enables quantification of properties like probabilities, rewards, etc. on CTMC models. And in our case, it is the quantification of energy consumption and data traffic. This is Then the verification is further performed using a Prism model checker. The results of the verification are then sent to the decision generator component. So the decision generator component sees the quality of service goals, takes the verification results, and it checks if there is any violation of course goals. If there is any violation, then it sends a reward in the form of a penalty to pattern selector. If there is no violation, it executes the adaptation through the executor component. In this way, pattern selector improves or converges towards optimal decision based on the feedback obtained from the decision generator. And we also can ensure that only feasible adaptations are executed. Our next step was to implement our approach on the NDR scenario. Of course, we didn't implement it in the real system, but we created a simulation of the system using carbon. During the simulation, the data was processed using Apache Kafka, and this was further used for creating the machine learning models using Keras. The data of quality of service as well as the sensor data was stored in Elasticsearch, and Kibana was used for visualization. We then, as we said, we used Prism model checker for performing the model checking. The whole approach was implemented on a Google Cloud platform, and it followed a layered architecture. Now, we want to test our approach and see how well it performs. So for this, we computed its effectiveness and efficiency by answering the four research questions. The first two questions correspond to effectiveness, and the second two questions corresponds to efficiency. Now, as I said, we implemented the whole approach in Google Cloud Platform, and we used Poisson distribution for simulation. This was done based on the real observations, and the experimentation was carried out for a period of 24 hours. Now, what are the evaluation candidates? First, we have three candidates, which are the basic patterns themselves, and then we have RL, which uses just the Q learning, and then we have model checking, which just uses model checking without any machine learning, and then we have RLMC, which uses the combination of both machine learning as well as model checking. The parameters used are, we wanted the energy to be between 6 and 10, traffic to be between 2500 and 3000. We used a horizon of 1 minute with a decision period of, horizon of 10 minutes with a decision period of 1 minute. So, how effective is the approach with respect to satisfying the overall energy and traffic goals? Well, we can clearly see that our approach RLMC consumes around 851 joules, which is less than the other approaches except for CO. But we can see that CO consumes more traffic than RLMC. On a whole, we can also see that the utility score of RLMC is much higher than that of any other approaches. Also, we have these parameters max dV, min dV, and EV. So max dV basically denotes the number of violations with respect to the maximum data traffic threshold, min dV with respect to the minimum data traffic threshold, and EV with respect to energy. We can also see that these values are also very less for RLMC, which proves that it is very effective with respect to the overall goals. Now, if you this graph further denotes the normalized values of what we saw, here we can clearly see that how RLMC is good in balancing energy consumption and data traffic, and this allows it to maximize the utility score with respect to other approaches. Now, how much does the model checking along with ML improves the satisfaction of goals? We can clearly see that RLMC initially starts very close to RL, but as time progresses, the gap between RLMC and RL keeps increasing. This is because RLMC is able to learn fast and converge towards optimal decisions at a faster rate because of the help offered by the model checking component. This is a clear indication that model checking contributes in an immense way for the improvement of RL itself. Okay, then what about the efficiency of adaptation? Here we actually plot the number of corrections made by the model checking component while an adaptation is performed. We can see that on an average, the number of corrections performed are very less. It is close to 1, but there are some instances where the number of correction is as high as 6. But this kind of corrections allows the RLMC to learn better and better. And since the number of correction is very less, we can say that the adaptation on an average is really efficient. Now, what about the computation overhead of adaptation? The approach takes 2 seconds for executing the adaptation, where the reinforcement part takes just 0.23 seconds and the model checking takes around 1 second. So, which is quite understandable. So the main overhead is model checking part, but we need to remember that this is just with respect to this case study. Also, what we need to remember is this is a proactive approach. So if we just increase the horizon, we can in fact take how much our time we want to perform the adaptation without hampering the existing execution state of the system. Okay, so concluding, we found out that using a combination can provide more optimal adaptation, and we found out that our approach in general performs better than traditional techniques. We also believe that we are one step closer to self-adapting ML system, where the ML system itself can adapt based on the verification results. Future work, we want to initially focus on the scalability part. We want to experiment with more coarse dimensions and different architectural patterns. We also want to see how we can handle issues with forecast accuracy, work on more fine-grained topologies, add a fail-safe strategy, etc. So that's it from our presentation. Thank you for attention. Feel free to write to us if you have any queries. Thank you.